Hi, my name is Ryan O'Hara. I'm a junior here at MUD, majoring in math, CS, and environmental robotics. This summer, I researched ways to introduce magnetic folding to origami microrobots. So let's do a little bit of background first. I worked up in Dr. Sawyer Fuller's University of Washington RoboFly lab. And this lab's primary focus is to develop affordable microrobotic systems for use in disease monitoring and atmospheric chemistry. To define a few of these terms, microrobots are basically any robots that are down at the micro scale. They're incredibly small, versatile devices that are capable of being used in a wide range of applications. Unfortunately, a lot of modern microrobots are prohibitively expensive to produce and maintain over a long period of time. They require expensive manufacturing technology, laser technology, and in general are prohibitively expensive for low-income communities. My project was primarily based around decreasing this barrier of entry. I hoped to use magnets and just basic magnetic principles to introduce a way to allow these microrobots to self-fold and self-create themselves. This decreases the need for incredibly expensive manufacturing technology and in general makes this incredible technology more available for lower income communities in countries all across the planet. And this central mission was kind of really the thing that drove me to work with the University of Washington in the first place. I really resonated with Dr. Fuller's mission to bring microrobots to communities around the world. I think science is best when it's applied to the real world and used to solve the issues faced by people who might otherwise not have the resources to solve those issues. And I think that kind of by decreasing the barrier of entry around microrobots, this research really has the potential to make the world a better place and really improve the lives of people all across the planet. So now I'll go into my research a little bit. I basically kind of took the approach of cell biology when trying to design the best way to introduce magnets to microrobots. As we know, magnets basically have two separate poles on them, call it a north pole and a south pole. And two similar poles will repel from one another, whereas two opposite poles will attract one another. And when you kind of take this into account, you can create an almost like energetic, quote unquote, field of how different magnets are going to work. Two opposite magnets that attract one another are going to be energetically favorable. Right? The magnets are naturally going to want to come together. Therefore, anything that those magnets are attached to will also be drawn together. You'll see the opposite happen when you have two similar magnets nearby. Those magnets don't want to come together. Therefore, they're going to be incredibly repulsive and it's going to be energetically unfavorable. In other words, any structures attached to two of the same magnets aren't going to want to come together. They're going to be as far apart as possible. And in cells, you see this exact same thing happen, right? When a protein folds inside your cell, the first thing it does is produce just a very long line of amino acids. And then kind of based on various properties of the amino acids, it folds itself into the lowest energy or most energetically favorable conformation possible. I wanted to do the exact same thing here with these robots. I wanted to put magnets at the exact right locations on the robot so that with nothing but a little bit of random motion, the robot would naturally and continuously fold itself into the kind of most energetically favorable position possible. If this energetically favorable position was the exact same as the position we wanted the microrobot to be in, and the exact same sequence of folds that we wanted to happen, then you have effectively created a way to self-manufacture microrobots. Now, this project has a lot of kind of longer standing applications and really kind of improves the use of microrobots around the world. Self-folding would allow for quicker and more efficient manufacturing of microrobots. Would allow for on-the-fly morphology changes. For instance, if you have a microrobot that wants to go from a longer conformation to a shorter conformation, the use of magnets placed at specific locations around the robot would allow it to do just that without any sort of human external interaction. It also increases the range of microrobot implementations. Like I talked about earlier, this would dramatically decrease the cost of creating microrobots, which allows more communities and countries around the world to take advantage of this technology. Finally, it removes a lot of the human error in fabrication by doing everything naturally via magnets rather than manually with, individuals kind of folding the robot up themselves. And in general, microrobots have a very wide range of applications that makes this valuable research to pursue. A lot of scientists have identified uses of microrobots in everything from climate cleanup, environmental monitoring, disease monitoring and analysis, small-scale manufacturing, human health, and general disease treatment and monitoring inside the human body. The potential of this technology is nearly limitless, and it's absolutely worth finding ways to decrease the barrier of entry around it so that everyone could take full advantage of microrobotic systems. So I started my summer by trying to create a sequence of magnets that would allow me to do a very simple 90-degree fold. I call this the single hinge model. And you'll see on the screen in front of you that I have various regions designated either red or blue. Red regions are north, are magnets with their kind of north pole facing outward, and blue regions are magnets with their south pole facing outward. In other words, two red magnets are repulsive, but a red and a blue magnet are attractive. And I found that kind of using this configuration, right, where you have opposite magnets on either side of whatever fold you want to create, you could very easily create a 90-degree fold, again, with nothing but a little bit of random motion. These magnets will naturally pull towards one another, which will in turn take your structure and create and hold a 90-degree angle. If the magnets are spaced properly back from the hinge, they'll then hold this 90-degree angle pretty much into perpetuity. I found this to be a very, very successful approach, so I tried scaling it up to some more advanced systems. Later in the summer, I tried to create the cube that you see on the screen in front of you. And you'll see in the image to the left that, again, I just had a sequence of 90-degree folds, each one of which had a opposite polar magnet on either side of it. And as seen on the right, whenever you introduce a little bit of random motion to the flat model on the left, this structure would fold itself up into a cube. And this was highly replicable. I never had any issues with the wrong magnets attracting to one another or the cube falling apart. It created a very stable, consistent structure. From there, I then tried to apply these principles to the actual RoboFly, the premier device used by this lab. So I printed out a cardboard version of the RoboFly and did the exact same thing. I just kind of found where every fold on the RoboFly would need to take place. I placed magnets, again, with opposite polarities on either side of these folds, put a little random motion in there, and just as with the cube, found that I was able to accurately and reliably fold the RoboFly from a perfectly flat sheet of cardboard up into the 3D model you see in the picture right there. So despite the success of my summer, there is quite a bit more work that has to be done to really bring this research into the real world. Number one is finding ways to apply these magnetic systems at the micro scale. I worked on the macro level. I used bigger magnets. I used kind of larger cardboard cutouts of the various devices that I wanted to fold with. This is primarily done for just kind of ease of magnet placement and ease of collecting data. And while many of the principles I discussed earlier should apply down to the micro level, more research does have to be done to make sure that's actually the case, that changes don't have to be done. Beyond that, I want to look a little bit more into the specific magnet types that are used. For instance, the magnets that I used at the macro level might not be applicable at the micro level. They might be too strong. They might not function the exact same way they did at the macro level. So I would have to be researched a little bit as well. Finally, there are some different angle types I want to figure out as well. I was able to find how obviously 90-degree angles worked as well as acute angles. By kind of pulling the magnets a little bit closer together, you can pull that fold beyond 90 degrees and kind of hold a continuous acute angle. However, I couldn't figure out how to make obtuse angles or anything beyond 90 degrees work well. So future researchers have to dive a little bit more into this and find ways to use magnets to hold these greater than 90-degree angles in place. But overall, I had an amazing summer and want to kind of give a couple quick thank yous to Dr. Sawyer Fuller for sponsoring me and allowing me to work in his lab, the University of Washington's RoboFly lab in general for giving me access to the technologies, research, and kind of team that I used to make this project happen, Harvey Mudd College and the Ben Hoop Memorial team for sponsoring my summer and giving me the scholarship money that I needed to finance my time up in Seattle. Thank you so much for listening. Hope you enjoyed listening and learning about my research. And again, I'm incredibly grateful for the opportunity I was given. Thank you so much.